Let's get the meeting started. Hi, everybody. Welcome to the Fast Code Seminar. Today's talk is one in a monthly series of virtual talks on the latest topics in the theory, practice, and teaching of software performance engineering. My name is Bruce Hoppy. I co-chair the organizing committee for the seminar, and I lead the community outreach for the larger Fast Code project of which this seminar is a part. Before Roberto introduces our speaker, I'd like to take a minute to let you know about the Fast Code Seminar and the larger Fast Code project. I am putting a link into the chat in case you want to follow along and look at the Fast Code website. Fast Code is an open source community dedicated to advancing software performance engineering. You can learn all about Fast Code by visiting our website. And this seminar, as you can see, is one of our featured events. Someone needs to mute there. You can see previous speakers. And you can also see that in addition to Mike's talk today, we have Renato Wernick scheduled in July. We're going to be scheduling lots more speakers after that. And down here at the bottom is some encouragement. If you have ideas about a speaker who would be a great fit for the Fast Code Seminar, we would love to hear from you. We being myself and the rest of the awesome organizing committee, Kuba, Roberto, Christian, Julian, and Ihan. In parallel with the Fast Code Seminar, I'm going to scroll up here. We also have a blog that is running on Substack. You can see some of the posts. And these are all meant to make software performance engineering accessible to a broad computer science audience. And if you have ideas about work that you think would be great to promote related to software performance engineering, I would really love to hear your story and help you write about it and promote it on the Fast Code blog. There's other ways that you can get involved. And you can click on the Get Involved page and see some of those. I'm going to skip over the details because I want to leave time for our great speaker. So I'm going to turn it over to Roberto to introduce our speaker and the seminar.
All right, thanks, Bruce. Hi, everybody. Thanks for joining. This is Roberto Palmieri. I'm an associate professor at Lehigh University in computer science. So I'm really happy to introduce our next speaker, Dr. Mike Spear. He is an associate professor in the same department. We are colleagues here at Lehigh. There's a long list of accomplishments that Mike broadly works in the programming language and distributed computing area. He got his PhD in 2009 with Michael Scott at University of Rochester. Interesting, he has an MBA. Not super typical for a computer scientist. Mike told me to share something fun, and I keep saying, when in 2007 I joined Lehigh, I figure since he was keep rejecting my papers, I might as well have him as a conflict. So he cannot review my papers because we are from the same institution. So anyway, I'm happy to introduce Mike. Floor is yours. Just a word about Fast Code. I got involved in Fast Code last year. I'm involved in the outreach part, and I invite everybody to look out for the new initiatives that we're organizing on activities, and as well as proposing new speakers. Mike, you're muted.
How about that? Now
All right, we got it.
Okay, so I think we've satisfied the first requirement of a Zoom meeting, which was somebody was on mute when they weren't supposed to be. I'm glad I got to be that person. I'm especially grateful, though, to be here, and I'm very grateful to everyone who's taking time out of their day to attend this talk. Hopefully you don't find it too disappointing. Especially because you're probably looking at this title and thinking, wait a minute, didn't we just hear something about this last month? Are we getting yet another concurrent data structure talk? This has been a hot topic for several years, and Guy's work is certainly some of the absolute best that's out there. And so what I'd really like to ask you to do during this talk is not listen with that ear towards what's better this time than last time, but instead, hopefully what you'll see from this talk is that there's been a lot of exciting research taking place in this space. And I think we are at that point in time where we can look beyond individual and specific contributions and instead start to say, what are the big picture lessons that we can take away from this? And ideally, are there big picture lessons that we can take away from this that are going to enable us to bridge the gap from research to practice? Are there things that are finally ready for prime time? So again, don't ask, how does X compare to Y? But instead, how do X and Y and Z make my job easier and make my job more fun? And so kind of the three big main takeaways that I'd like everyone to hopefully agree with me by the end of this talk about are, first of all, that multi-word atomic operations don't need to be scary. I think that with all of the research that's happened so far, we're at a point where they're actually fast and easy and maybe even fun. Secondly, a lesson for the designers of synchronization abstractions and maybe abstractions in general, that if your goal is to reach experts, it's important to let the experts see inside of the box. It's so tempting for us to be concerned about protecting our abstractions and not recognize that we don't always know the best ways that those abstractions can be used. And then the third thing for concurrency or for concurrent data structure designers is what seems like a very low-level point, except for how fabulously liberating it is, that we should embrace internal linking. I think if we put these three things together, we're at last in a place where programmers can focus on what structure makes the most sense for their program, instead of focusing on which synchronization mechanisms limitations are the least undesirable for the problem I'm trying to solve. So the outline that I've prepared for this talk, I'm going to just do a brief vocabulary review. You don't have to agree with my definitions, but I at least want you to know what I mean when I say certain words. Then I'm going to give what maybe you want to think of as a historical fiction of memory transactions or transactional memory. From there, I'm going to move into two different topics, presenting two different research papers, and then use those to draw some conclusions and share some thoughts about the future. So let's dive in. And when we do, I think the first term that I hope everybody is comfortable with is this idea of linearizability. The key point to linearizability is it's a way to reason about the correctness of concurrent executions. And if we can say that an implementation only produces linearizable execution histories, then it is a linearizable execution. So we're trying to explain concurrent histories via equivalent sequential histories. We want to say, if the concurrent program did X, I can imagine a sane sequential program that would have interleaved the operations of the various threads one at a time and had the same outcome. And so in general, there are two broad requirements here. The first is that each method or operation happens between its invocation and response. So there's some notion of program history, and the second, or program order. And the second is that each method or operation appears to happen at a single unique point in time, separate from the points in time when any other methods or operations by other threads happened. And so if we imagine an execution here where we've got three threads, thread one is enqueuing A and then dequeuing from an empty queue. Thread 2 is enqueuing B, and thread 3 is performing a dequeue. If we identified the times when each of these operations happened with red, then T1 would happen before T3, which happens before T2, and T3 would dequeue A. But if we use the yellowish colorings, then even though T1 started first, T2 could happen first, and therefore when T3 performed a dequeue, it would see B rather than A. We could also use the blue colorings because that's equally valid, and we could see that T3 observes an empty queue. So again, the takeaway here is there are lots of possible histories that could happen in a concurrent execution, and if they can be explained using these rules, then the implementation is linearizable. Similarly, if we look at the dequeue that T1 could have, it could also dequeue A or B or empty. But if you look carefully, hopefully you'll agree that T1 can't return empty if T3 also returned empty. And then finally, all threads have to agree on the order of the enqueues in what they're in terms of what they see from their dequeues. So if you're comfortable with this idea, then the next term very closely associated is the idea of a linearization point, which is that moment in time at which some instruction by some thread, let's call it TZ, does something that causes an in-progress operation by some thread TX to happen in the global history. And I've framed it in this way because it's surprisingly nuanced. X may not equal Z. Sometimes an instruction by one thread, which could be a read, a write, or an atomic read modify write operation, will make the operation by some other thread formally and officially and finally happen. The other complexity here is that there might be more work to do after the linearization point. It doesn't necessarily have to be the first instruction or the last. It could be somewhere in between, and it depends on the sophistication and cleverness of the algorithm. Normally, when people are thinking about lock-free programming and they think about linearization, they assume that there would be a compare and swap instruction that linearizes the operation. That's very common. But it's also worth noting that locks do lead to linearizable programs because the red acquire here and the yellow release, we can effectively say that at any point in between the acquire and release in a correctly synchronized program, that's when the operation happens. And so in this picture here, where I've used the length of the red circles to indicate how long they spend waiting for the locks, we can see that a lock acquire and a lock release, we still are able to produce a history that has an equivalent sequential history. If we're being completely precise here, it's worth noting that there's some subtlety to this point about locks. If the critical sections access atomic variables inside of them, or if they use condition variables, then it's not so straightforward. But if they don't, then we have an easy argument for how a lock-based critical section can lead to linearizable code. And that argument even extends all the way to the use of two-phase locking. So for example, we can say that at any point from when the last lock is acquired until the first lock is released, anywhere in there, we could assign the linearization point. But if we start to focus on locks, I think everybody in this call knows we're going to get ourselves into trouble. Because if we acquire locks just in order to be able to read data, it's going to be horrible for performance. We're going to turn reads into writes. We're going to add more instructions. We're going to have a terrible impact on caches. And if all we were worried about was protecting a read from a concurrent read, we don't need locks to do that. Simultaneous reads don't result in a race. On the other hand, we do have a big problem if we don't acquire locks before reading and we want to be correct in the face of writes. And so if we have concurrent writes and we don't acquire the lock before reading, well, then the language level memory model might just simply declare that there is a race and therefore the program is erroneous and we can have undefined behavior. But we also have to be worried about very practical concerns. If one thread is trying to read an object at the same time as another thread is performing writes and reclaiming that object, then is it possible that the reader will fall into an ABA trap because it's reading a value that's actually not what it thinks it is? Or worse, could that object be handed back to the operating system in a way that causes the reader to have a segmentation fault? So on the one hand, we know that we don't want to lock in order to read. On the other hand, we know it's kind of tricky to do that correctly. And I think the community has settled on three things that work together to solve this problem. The first is that anything that's read or written without holding a lock has to be an atomic variable. By definition, if it's an atomic variable, there's not a language level race. But also by definition, a read of such a variable won't be stale and it won't be reordered incorrectly. If we look under the covers, of course, we know that optimizing ordering for atomics is a dark art, and the performance really matters if we're not on an x86 processor. But for now, let's not worry about that. If we make things atomic, we're 1/3 of the way towards being able to do optimistic accesses. The second thing is to address that segmentation fault problem. We're going to need some sort of out-of-band safe memory reclamation algorithm. I saw Ajay Singh on the call here. I know he's done a lot of work on that, as have many other people. But in general, what this means is we're going to have some operation block concurrent threads from reclaiming anything that that operation might be accessing for the duration of its operation. And there's been a lot of work to try and optimize this in order to make sure it scales, to bound the amount of garbage, to narrow just how much stuff is being blocked from being reclaimed. But we don't need to worry about those details today either. And the third thing that we typically do in order to make sure that optimistic accesses are safe and the resulting programs behave correctly is to introduce some notion of speculation and rollback and validation and often even marking. And I realize that the words on this slide here are quite vague. I say make sense, but if I were to try and go into very precise wording here, I could probably give a whole talk just on speculation and validation and marking and how they're used in different structures. But the point here is that if one is reading through a data structure without looking at the locks and seeing what's actually in the data structure and what's being operated upon, there's going to be some point at which that operation needs to double check that everything it saw makes sense. And if not, that operation might have to go back and try again. And in particular, when something is being removed from the data structure, it may be necessary to perform an extra write just for the sake of ensuring that the validation by a concurrent reader is successful. So on the one hand, hopefully everybody is comfortable with this vocabulary. On the other, it may sound like it's a little bit too complex. And certainly the research community did have many people who agreed that it was very complex, because since about 1993, there's been a lot of work on this idea called transactional memory. And so I'd like to just kind of go into a brief historical fiction about this. Some of the details are not going to be exactly right. Some of the timelines are going to be a little bit out of order. But the rough idea here was back in 1993, the term transactional memory was coined as a hardware concept where the only goal was to simplify the task of creating non-blocking data structures. And so in code, we could think about this as a begin transaction. You do your operation, you commit your transaction, and you enjoy your result. Behind the scenes, the right way to think about this is if everything stayed in my cache while I was performing my operation, then no other processors could have seen it. So I guess it must have been atomic. Of course, this means changes to the cache coherence protocol, and verifying caches is a tricky thing. It also means we have a problem if the operation is too big to fit in the cache, or if different operations have pathological conflicts that mean that everything is live locking and failing to make progress. Another issue here is, since there's some amount of speculation and the possibility that some things will be read and then ultimately a conclusion will be made that rollback needs to happen, we have to be concerned about what might happen if there's a transient inconsistency in the middle of a transaction and that transient consistency causes a hardware fault. And so in general, hardware transactional memory swallows or hides those faults and just lets them manifest as an abort. But if verifying caches is tricky and hiding transient inconsistencies is tricky, and we do all of this in hardware, we can get into a situation where we wind up with an accelerator for cache-based side channel attacks. And that's exactly what we saw with Meltdown. Fortunately, we also have this idea of software transactional memory, which essentially says that we can do all of this management of speculative state and tracking and validation in software. And we can do this by just exposing a very simple API for beginning transactions, committing transactions, and then every read or write of shared memory gets replaced with a function call that performs that read or write while also interacting with some metadata that's associated with each memory location. The earliest transactional memories were non-blocking. Some of the most fascinating and algorithmically sophisticated transactional memories are non-blocking, but it's okay for us in this talk to think of transactional memory as really being a sort of two-phase locking with optimistic concurrency control. We can imagine that some lock with a version number embedded in it is associated with each location, and reads record that version number before they access the location and save it in a thread local log. Writes acquire the corresponding lock, which also changes the version number before they modify a location. And then at commit time, a writer needs to go through and validate that all of the reads were correct, finalize the writes, and release ownership. For arbitrary and complex operations and data structures, though, it's important to periodically validate as well in order to make sure that each time a new read is added to the working set of a transaction, that read is consistent with everything that's been seen beforehand. Otherwise, we can have transient inconsistencies, infinite loops, and other messes. So this works. The problem, however, is that this has a propensity to be very slow. And so much research, especially since about 2003, has been focused on how to make this fast. First and foremost has been effort to reduce the cost of validation. A couple that I'd like to highlight here are DSTM, which introduced this idea of early release to selectively forget things that were read so they no longer have to be validated. TL2 brought about this idea of a clock, which meant that when locks were released, all of the locks for a transaction were released at the same time. And any two transactions that were releasing locks, the times at which they released those locks would be totally ordered. TL2 also brought about this idea that read-only transactions could leverage that clock in order to not need to do any logging or validation for read-only transactions. And Pascal Felber, in a journal article, which actually dates back several years prior, brought about this idea of elastic transactions that mean that we only need to remember a few reads before the first write, and most data structure operations will still be correct. There's also work on limiting the cost of per-access instrumentation and an alphabet soup of different kinds of metadata and uses of metadata and whether we should use undo logging or redo logging and all sorts of other great ideas for trying to reduce the cost of transactional memory. Unfortunately, as people were getting more and more excited about transactional memory, we also became acutely aware that multi-core was not going away and multi-core programming was going to be hard. Scale-up programming was going to be a challenge. And so researchers started looking at ways that we could use transactional memory to do more than implement individual data structures. A very important observation from Tim Harris was that we can put multiple operations into a single transaction, but there's this inherent composability to transactions. A scarier observation that I think Virendra Marathe was at the forefront of discovering was that when we start thinking about how to use transactions in real-world code, and especially how to replace locks with transactions, we wind up with this privatization problem where we try and use a transaction to transition data from a shared state to a private state. And now, if there's a speculative operation that's still accessing that data while the post-transaction call to F in this example is running, then we can have a race manifest. And that means we can get into a big mess. In addition, not on the slide, is just the observation that there was a sense that it needs to be kept easy. A compiler needs to do all the work with as little programmer intervention as possible, which means that the compiler was responsible for deciding how to associate memory locations with the synchronization metadata and how to use that metadata. And everything was hidden from the programmer. I think we made a big mistake. And I think that the mistake we made was that we were trying to solve the wrong problem. I was one to say this, and I heard many others say that the average programmer is not up to the task of writing concurrent code. And if we look at how many programmers have been using cloud resources for the last 15 years, I think we have to conclude they didn't need to write concurrent code. The cloud and scale out with high-level languages made it possible to harness multi-core systems without thinking about or worrying about concurrency at all. And so while especially the transactional memory research community was laser focused on how to make an easy-to-use abstraction for the average programmer wasn't interested. In retrospect, we should have been focusing on expert programmers and not worrying so much about how to hide the details of how the transactional memory works, but instead recognizing that experts might want to safely use the transactional memory's internals in ways that we never intended. It's worth observing that entire products like MemSQL are built around a single scalable data structure. It's not unreasonable to think that the cloud doesn't need privatization. It needs extreme scalability for the common case. And that's not what we were looking at. So from here, I think we have to admit, transactional memory looked like quite a bit of a failure. However, there were lots of great ideas lurking in there. And some of those great ideas have continued to gain attention from researchers. And as they have, I think what we've all come to is an observation that there's really some great stuff that can be done here that delivers simplicity and performance. The first paper I want to talk about in the remainder of this talk is this paper about exoTM and software transactional multi-word compare and swap. This is not the title of the paper. It's a mouthful, but it's better than the title of the paper. You're encouraged to try and go find it if you'd like. But the key observation in this work is that we had built something so complex that we lost sight of what was important in it. And so on this slide, what I've tried to do is take everything that goes into the language level transactions in the transactional memory technical specification that was published in 2015 and implemented in the GCC compiler toolchain, and split it based on whether it's API, which is that top bar, or whether it's the internals of how it's implemented. And then from left to right, you can see that we've got three different sections. On the far left are the lowest level mechanisms that relate to how we achieve the synchronization. In the middle is a set of API calls that a programmer could use if they wanted to roll their own transactions by hand. And then on the right are incredibly expensive abstractions that are required in order to make these transactions work in a general purpose programming language. So it takes all three of these columns to have language level transactions, but there's so much untapped potential on the left-hand side. Let me just briefly review what's on the left-hand side, and then I'll explain what I mean. So we're going to say that an ownership record is like a spin lock. If it's even, the lock is available. If it's odd, it holds the ID of an owner, and the lock is owned. Even values will be monotonically increasing, representing new version numbers. There's also going to be a clock that assigns start times to operations, and also that assigns commit times to writers, such that every writer is most likely going to have a unique commit time. And we don't need to worry about the details of when that's not true. This clock, of course, is also going to be monotonically increasing. And what we'll do is we'll use this innovation from TL2 and say all of the ORECs released by an operation are assigned the corresponding commit time. That clock could be a shared memory clock. One of my PhD students back in 2013 worked with some engineers at Intel to figure out how to use the RDTSCP timestamp counter correctly as the clock instead of using a shared memory clock, which avoids a scalability bottleneck. And then third of all, we're just going to assume, even though it's not here on the left-hand side, that there's a separate safe memory reclamation algorithm in place. This is not much. There was no discussion of where to place the ORECs or how many ORECs need to be there. There was no discussion of program data or how to read program data in any of this. It's just the bare minimal necessary piece in order to implement these different transactional memories. And so if you look at this slide, what you'll see is I've put the entire algorithm for implementing this synchronization facility on one slide. It's not here because I want people to read it and understand every line, but rather to observe that on one slide, without using a ridiculously small font, we can see the entire synchronization component at once. In fact, this is actually more than any one STM would need for two reasons. First, in the bottom left corner, the release ORECs algorithm actually has three different code paths in it to correspond to whether we want to do undo logging or redo logging or commit time locking. And then on the right-hand side in the bottom, the acquire by value and aggressive acquire operations have no purpose inside of a traditional software transactional memory. So very little is needed here, and everything else that goes into a transactional memory sits atop this. What's most important about this is that if we protect things correctly using language level protection mechanisms, we don't have to hide this. All of this can be exposed to the programmer, and if we expose it in the right way, we can give the programmer abilities that the programmer didn't have before. So just to summarize what you saw on the preceding slide, the innovation is not the algorithm, but in the way it's expressed and protected. In particular, there's a nice safety property, which is that even if threads can see the values in ORECs, even if a programmer who's using this is able to peer all the way down and see the OREC, if they're obeying language level protection mechanisms, no programmer, no thread can put an arbitrary value into ORECs. The only values that can go into there are the ones that a TM would want to go into there. And so if this seems boring, that's great, but there's so much power in being able to see unacquired OREC values and control the location to OREC mapping. And so that's what I really want to dive into now. Before I do, I just want to point out that even if we could solve the problems with hardware transactional memory accelerating cache-based side channel attacks, it's not necessarily the case that hardware transactional memory is going to be able to do very much with us. And so if you're thinking, why focus on software transactional memory when we could have hardware transactional memory? I want you to notice a few things. First, The most expensive part of software transactional memory is the logging and the validation. So logging the read set and validating it at commit time. I already showed you or told you that in TL2, it was shown that that overhead can be ignored completely for read-only transactions. Secondly, the least avoidable part of software transactional memory is the writing, but writing isn't exactly cheap in hardware transactions either. The boundary overhead alone for starting up a hardware transaction is roughly on par with 3 to 5 compare and swap instructions. And if you start counting, the average height of a skip list node is 2, and the average depth of a node in a balanced tree is 2. So if we need to get 3 to 5 CASs in order for HTM to be on par with STM performance, we may not be able to get there very easily if we can be smart about the other overheads. And then lastly, I want to point out that all transactional memories struggle with the high cost of aborts. There's always wasted recomputation if an operation is near its completion point and fails and has to start from scratch. So on the previous slide, I said we get tremendous power if we can see the value of OREX, if we can expose that to the programmer. I want to justify that claim now. We can use ownership records or the values in ownership records as proofs. In a correctly synchronized transactional program, no shared value is written without first acquiring its OREC. And also, in a correctly synchronized transactional program, an OREC cannot be returned to its old value unless the corresponding data was not written. That is to say, I could acquire a lock, not change the data, and release the lock back to its old value. But if I acquire the lock, write a new value into the location, and then unwrite that value, any correct transactional memory requires that the OREC be set to a new value when it's released. So if we take these two rather simple properties and combine them, we can see that if an ownership record has not changed since the last time a thread inspected it, then the data associated with that ownership record also has not changed. In order for this to really hold, we do need to decouple the safe memory reclamation boundaries from the transaction boundaries, but that's a minor point. The important point here is that if the programmer can see the ownership record, the programmer is able to start drawing conclusions about what has and has not changed. And this gives us two very powerful new optimizations. I'm going to refer to this one as the software transactional multi-word compare and swap. The SG5, the group that has been building the technical specification for transactional memory in C++, has had many debates about whether or not it would be possible to read lots of locations without a transaction and then just use HTM to perform a multi-word compare and swap effectively to make all of the changes that an operation would need. And this doesn't compose with the transactional or with the C++ memory model. But we know that read-only transactions don't need to log. We know that data structure operations often involve a read-only prefix, and we know that the correctness of the read-write suffix after that read-only prefix typically only involves a small number of locations. So what this means is that a programmer could split an operation into a read-only prefix that concludes by leaking a set of address and OREC value pairs, and then can pick up from a read-write transactional context that uses the check val and acquire val instructions on the preceding slide to only allow the transaction to proceed if those OREC values didn't change. Furthermore, if the value of the OREC doesn't matter, then it can just use this raw acquire if consistency isn't needed there. And so if we put all of this together, it means that we have the power to split an expensive transaction consisting of a long read phase followed by some acquisitions, followed by a validation, with a very fast and optimized read phase, followed by a tiny suffix transaction that just accesses a few locations by acquiring their ownership records, performing writes, and committing. Going just a step further, in a lot of cases, we don't even need to do any write logging or as we're completing that suffix transaction, because we can acquire all of the locations before we perform any of the writes. So putting this all together, what we wind up with is the ability to take one data structure operation, break it into 2 data structure operations, and then remove all of the overhead from each of those data structure operations. At some level, it still fundamentally feels like transactional memory. But at another level, we've taken all of the overheads that are hallmarks of transactions and gotten rid of them just by letting the programmer optimize their code around these ownership record values that, for the longest time, we all thought we needed to not let them know existed. Now, that takes care of 2 of the overheads that I described, but we can also address other overheads. So I want to start at the bottom of this slide and this question of recovering from aborts. I said that STM and HTM both suffer from the cost of recomputing a transaction after an abort. But if we think specifically about data structures, then can't we take these pairs of addresses and ownership records, and if the programmer knows how the ORECs are associated with the addresses, can't the programmer say, for example, well, I was on this node of the tree, and when I got to that node of the tree, the ownership record value was X. So after an abort, if I could check that node and see that the value was still that, then I might as well just teleport to that position and keep executing my transaction from that point. If programmers can do that, then for all intents and purposes, we've mitigated the cost of aborts by letting transactions resume not from the beginning, but from some intermediate programmer-defined safe point. So we can use this idea of snapshotting OREC values in order to make that work. Now for lists, this is very clean and easy because we only ever need 1 snapshot in order to recover, though we could keep a handful of them around for the sake of having some backup plans in case one fails. For trees, it turns out it's a little bit more complicated, and we might need to keep an entire spine of address and OREC pairs and then resume from the longest consistent prefix. But in general, we've solved the remaining overhead of transactional memory. There's also a constant time overhead that we could be concerned about because every time we read a location, we're supposed to interact with the metadata. But 25 years of history with concurrent data structures shows that we can have consistency and linearizability without doing that by leveraging what the lazy list refers to as optimistic weight-free traversals. From a memory model perspective, the fields of these data structures are already atomic, so we don't have to worry about races. If the writing phase does not perform undos, then we also don't have to worry about out of thin air reads from a speculative operation. And so it turns out we can get non-negligible savings, fewer aborts, and identical overheads to non-transactional data structures just by being careful about how the programmer optimizes their read-only traversals. And we essentially get something akin to the weight-free optimistic traversals of concurrent data structures. So hopefully you're starting to think that maybe there's some potential to this. If so, the next question is, how hard is it to use once we start doing all of this? In this slide, I've just put up the actual C++ code for the implementation of searching and inserting in a linked list. Again, I don't want you to read all of this code. Instead, what I want you to notice is that the right-hand side, where the algorithm is actually implemented, is only a small amount of lines longer than what we would have needed to write in the case of a sequential list algorithm. And most of that has to do with dealing with the possibility of reading an ownership record and needing to jump back up to the top of a transaction. So in general, we don't need to be worried that this is going to make programming substantially harder. And so the trade-off then becomes, is the performance good enough and is the reasoning about correctness easy enough that whatever added burden is added is acceptable to an expert programmer? I think the answer is yes. We're going to need to look at the performance to convince ourselves of this. But what we have found is that we've been able to take lots of concurrent data structures and lots of sequential data structures equivalent to those concurrent data structures and transform them using this methodology, delivering excellent performance. So in general, the methodology is you start with a sequential data structure and you ask, if this were concurrent, would it have sequential bottlenecks? If the answer is yes, this is the wrong talk, and we need to look to somebody else in the fast code community for what to do about that. But if the answer is no, then we can simply convert it to STM in a way that's going to be amenable to STM-CAS optimization, and then run it and see how it performs. In the same way as we don't jump to inline assembly until we know that we need to optimize at that level, there are levels of optimization that are available to us at this point. The first is to selectively split transactions into a read-only prefix and then a writing transaction. We can optimize those prefixes if we need to, and we can selectively convert the suffixes from STM to this STM-CAS style as needed. And the technique reminds me of a quote from Tony Hoare that there are two ways of constructing a software design. One way is to make it so simple that there are obviously no deficiencies, and the other way is to make it so complicated that there are no obvious deficiencies. We have found that using this methodology puts us in the former camp rather than the later, which is hopefully what everybody here is hoping for. I still haven't addressed the performance question, so let me just briefly do that. I'm going to just provide a snapshot here. This is somewhat routine and mundane. We're going to have two sets of charts, one with uniform randomly drawn keys and a workload that's 80% reads, and then another where it's 0% reads, and so an equal mix of insertions and removals. For maps, we'll use a key range of 1,000,000. We'll use a key range of 1,000 for lists, and this is all running on a machine with 48 cores, 96 threads. And what you'll see here is nothing especially interesting, except that these STM-based algorithms are not outperforming just other STMs. They're outperforming state-of-the-art concurrent data structures. And so we could start here with a linked list. And if you look at this linked list, the black line is a pure STM, which immediately falls into bad behavior. The red line is the lazy list. Dark blue is using STM-CAS. And as we employ these optimizations, we ultimately get to the performance of the lazy list. What's even more interesting, though, are the light blue lines. The light blue lines here represent a doubly linked list. Normally, we don't think about using double linking when we're implementing a concurrent list because that requires atomically modifying two locations, and we all know that atomically modifying two locations is hard. But in this case, it's not hard because multi-word atomic operations are easy now. And when we have a doubly linked list, we can get significantly better performance because there are fewer instructions on each iteration of the underlying loop. And then when it's time for us to remove or insert a node, we can be much more optimal in how we do it because we don't need to be concerned about the neighborhood of that node. We can find the predecessor and successor in a secondary transaction after the read-only phase is completed. Continuing along these lines, we also looked at a skip list. A singly linked skip list wasn't able to compete with the Fraser skip list. But when we had a doubly linked skip list, that is a skip list where at every level there aren't just forward pointers, but also back pointers, then we're able to meet and in some cases exceed the performance of the lock-free Fraser skip list. Again, a very exciting result. We took our approach and applied it to the Lou hash table, and then we compared the Lou hash table, which is a resizable closed addressing hash table. We compared that against a non-resizable hash table built by having a list of buckets where each of the buckets then held a lazy list. And in essence, what we found here is that adding support for resizing was free. At the same time, most of the optimizations didn't even matter. Snapshots, for example, don't mean very much when you've got small read sets and low contention. So we were able to take a sophisticated non-blocking algorithm for resizable hash tables and dramatically reduce the number of lines of code and get performance that's better than anything that we've seen before for this kind of hash table. And then finally, we also looked at a balanced tree. And here what was very nice was the ability to decide dynamically how to compute the suffix transaction. If an operation found that it would need to do an insertion or removal that would not require rebalancing, then we used STM-CAS, whereas if it would, we used STM instead. And doing things in this way and also benefiting from how STM lets us have in-place updates meant that we were able to achieve very nice performance, especially compared to existing lock-free data structures and transactional data structures. So I said at the beginning, and I want to reiterate now, the point of this is not to say technique X is better than technique Y. There are lots of good reasons for using things other than exoTM or STM-CAS, and all of these different ideas that are out there are wonderful. I think the most important point is that we've got quite a few techniques out there for doing multi-word atomic operations that are cheap and fast and easy to argue correct. We found that the data structures that we were implementing were easy to implement. And since we started from a nice, simple transactional two-phase locking approach, we were never worried that we had an incorrect data structure. I would go so far as to say there was actually a lot of joy in optimizing, even when we explored optimizations that didn't pay off. By the time that we had gotten very far along in this project, the students who were involved were starting to do rather aggressive optimizations. One of the most interesting I found was caching successor keys in every layer of the tower of a skip list node, because it halves the number of unnecessary pointer dereferences that need to be performed. And that sped up the data structure even more than what you saw in the preceding slide. For me, it was uncomfortable to think about double linking and all of these other changes, because I've been so hardwired to think one linearizing CAS is what it's gonna take if you're gonna get good performance. But we teach undergraduates to think about the structure of the data structure. We teach them to embrace internal linking if it's going to give them better asymptotic performance. And so for the remainder of this talk, I really want to emphasize thinking about this question: what benefits come from internal linking? And to do that, I'm going to tell a story about a recently developed data structure by my student, Matthew Rodriguez. This story goes back a fair bit. In 2013, in the Transactional Memory Technical Specification Working Group, Jens Maurer said that LRU caches were, in his opinion, a killer app for transactional memory. And it just sort of flew over my head. 11 years later, it finally sunk in when John Bentley was visiting Lehigh and observed that Claude knows how to write an optimal sequential LRU cache, but still doesn't know how to write a good concurrent one. And he proceeded to remind me of how you use a doubly linked list, and then you also have a hash table for getting into that list so you can find things quickly, and you get O of 1 overhead for everything. Of course, LRU has some fundamental scalability bottlenecks, but hearing this idea come up again got me thinking about what would happen if we took the same idea of using multiple underlying data structures that work together to provide a single external interface, and we instead applied it to ordered maps. Again, we shouldn't be afraid of synchronization. We shouldn't be afraid of internal linking. And we should look to the problem of implementing this data structure as a divide and conquer problem. How can we solve each problem independently of the other ones to eventually produce a comprehensive solution? I'm not going to share any code. I'm not even going to share a picture of the data structure because it is so easy to envision. Start with a doubly linked skip list. Augment it with a hash table that maps from keys to skip list nodes. And then keep the hash table consistent with the skip list at all times. That's it. If you do these three things for your standard create, read, update, and delete operations, the asymptotes turn out to be quite nice. Lookups are always constant time. If something is not in the hash table, return false because it's not in the skip list either. If something is in the hash table, you have immediately routed to exactly where the key value pair is and can return the value in constant time. Similarly, for updates, we either don't find it or we know exactly where to go to update the value. Half of removes and inserts are super easy. If we try and remove something that's not there, we never touch the skip list. And if we try to insert something that's already there, we don't touch the skip list. The only two that are at all interesting are removing something that is there and inserting something that's not. Since the expected height of a node is 2, removing something that is there is constant time. We find it in constant time, and then we do, on average, 2 operations to unstitch it at 2 levels. So this means that now we only have one operation, an insertion of a key that's not already present, that actually requires traversing through the skip list. I have not yet explored whether it would be worth redesigning the shape of the skip list based on the understanding that it's only insertions that will actually need to traverse the index. But even without exploring that question, we find that we get a very simple, easy to reason about, and fast data structure. Now, since we want this to be an ordered map, we also need to support point queries. So we need predecessor, successor, floor, and ceiling. If we provide a key to these operations that's already in the map, they're all constant time because we can move forward and backward in the doubly linked skip list. Otherwise, we fall back to logarithmic overhead. And so at this point, what's most interesting about this data structure is that we implemented the whole thing in about 4 hours. We didn't bother with STMCAS, we just used STM. The hardest part was bike shedding the names of the methods. I will say doubly linking in the skip list was necessary in order for us to get the fast removals that we wanted. But in general, this was a game. It was so easy to do. But of course, we don't just need point queries. We also need range queries, and we wanted linearizable range queries. So there's a nice, simple solution, which is to just do the entire range query in a single software transaction. In the worst case, it takes logarithmic time to find the predecessor of the first key because the first key isn't present, after which it's just order n, where n is the number of elements in the range to access all of them. And if we do this using read-only transactions, it's perfectly scalable. We can't really optimize it using any of those weight-free traversal techniques because we need to make sure that everything we read is consistent with everything else in order for it to be linearizable. But it was simple and it was fast. The only problem is that this doesn't work well for long-running range queries that are competing with very frequent updates that overlap with the range query, because then we have the potential for starvation. We knew that there's transactional contention management. We also know, though, that one more read is negligible in a read-only transaction and at the end of a writing transaction. So instead, what we tried to do is avoid multi-versioning, avoid adding contention management, and instead add a third object to the data structure. We'll call this object the range query coordinator. Before I go farther, I want to remind everyone, this is not about me trying to tell the world that we have the best range query implementation. There are lots of great range query implementations. Guy Blalock's group, Trevor Brown's group, Roberto Palmieri's group, and so many other groups have been looking at this problem and have found some really wonderful solutions. This is about having a good enough solution that's also very fast and very easy to reason about. And so I'm going to start with talking about what changes happen to those CRUD operations. We're going to introduce a queue and counter that all inflate range queries are going to need to interact with. And then we're going to have 2 more fields in each skip list node, an insertion time and a deletion time. Nothing about the hash table is going to change. Instead, when something is inserted, the operation needs to also check the insertion time in the RQC and write it into the node. And when something is to be removed, instead of unstitching it from the skip list, it still unstitches it from the hash table, but instead of unstitching it from the skip list, it sets the delete time to logically mark it as deleted. And then it adds that node to some list that the newest range query is going to be responsible for cleaning up when it's done. On the other side, we can get almost starvation-free range queries out of this because we'll perform the range query via multiple transactions. First, we'll do one transaction to put the range query into the RQC, essentially enqueue it and increment the counter. And then we'll traverse into the skip list by using the hash table, hopefully, or else having to traverse through to find a starting point. And then once we've found a starting point, it has to be a safe node. It has to be a node that cannot be removed physically from the skip list until this range query is done. Once we find one, we can start just using software transactions to span a small number of nodes at a time and moving across a few, and then a few, and then a few, and then a few like that. We can optimize this in some very nice ways. In particular, if we allow the programmer to see when aborts happen and deal with them explicitly, then anytime there's an abort, the programmer can simply use the preceding safe node as the checkpoint and resume from there to start a new span so that no node ever has to be processed twice. And then finally, when all is said and done, a thread will exit the queue and perform any unstitched transactions that are needed. If that queue is not if that query is not the oldest in the queue, it passes them forward in order to ensure safety. So of course, there's a question, which is better? The RQC is a contention hotspot if there are frequent small range queries, but not if there are frequent long range queries. It's absolutely necessary if there are long range queries and lots of contention, because otherwise there's going to be starvation. But we also know that the cost of a small query abort is negligible. And so the solution that we came up with, unsurprisingly, is to have a fast, slow strategy that falls back to the more expensive technique only when needed. This means in the common case, we're adding one more read, which is practically free to most operations, and not dealing with anything more than that. So now let's look at performance. And here we're going to look at a couple of things like the VCAS binary search tree, the VCAS skip list, the bundled skip list, all of which were enhanced with RDTSCP based on a paper by Olivia Grimes. We've also got, just for reference, an STM hash map and skip list for looking at CRUD operations. And in these charts, any thread can issue a CRUD operation or a range query operation. Range queries are 100 elements in the range, which typically means only 50 will be present. And a query is going to be counted as an operation, the same as any insert or removal. So the y-axis is a little wonky here. And the main takeaway is that this asymptotic acceleration does wonders for the CRUD operations. You can see in the top left chart that the CRUD operations, when it's an 80% read-only workload, are tracking perfectly with the hash table. And when we go to 50-50 insert remove, we're still significantly faster than anything else. Similarly, when we introduce range queries, the simple transactional range query approach works very well because the key range is large, the range query range is small, and so everything is very nice. But of course, this means I'm hiding the interesting question. So what happens when we have dedicated CRUD threads and dedicated range threads so that we're sure that there are going to be conflicts? In this chart, the x-axis is the size of the range query, and the y-axis for range is the number of processed nodes. That way, if we do 10 10-element range queries, we'll have 100. If we do one 100-element range query, we'll have 100, and the curves make a fair bit more sense. We didn't do anything sophisticated here. We just used 3 failures as the fallback to the range query coordinator. And what we found was that the number of aborts per successful fast path range query went from about 1.3 when queries touched about 1,000 nodes to 22 when we got to about 4,000 nodes. And when we started to touch about 8,000 nodes, the performance of the fast path dropped to 0. At the same time, we observed this nice trade-off where the range query coordinator contention ceases to be significant. And so overall, the trade-off is pretty nice. So again, the main takeaway here is not that this is the best ever. It's that the implementation took less than a day, except for the range query coordinator. And again, correctness was never a concern. The asymptotes were trivial to achieve because we thought about the data structure like a sequential data structure, and we didn't worry about the cost of multi-word atomics. And it was fun. We spent most of our time thinking about how to prevent contention, not how to get everything to actually linearize. Hopefully, most of the people who are listening to this talk know that they could do better. We have a simple fallback path. We didn't optimize cache locality. We didn't implement any fancy algorithms. We didn't take into account any a priori knowledge about keys and ranges. And we still got very nice performance without ever having to worry about correctness. And so this brings me to the end of the talk and to a reminder about the title of the talk, that it's time for us to renew our focus on the structure of concurrent data structures. I began with these 3 claims: that multi-word atomic operations are fast and easy, that designers of synchronization abstractions should let experts see inside of the box, and that we need to embrace internal linking, the same techniques that we teach undergraduates in order to make it easy to get good asymptotes should be available to programmers of advanced concurrent data structures. Shouldn't be looking at the charts and saying which is better. We should be looking at the charts and saying, if we've got so many great options for concurrent multi-word operations that are atomic and fast, then maybe it's time for us to change how we think about concurrent data structure design and focus on the asymptotes first. Stop worrying about the peculiarities of how to linearize our operations. Looking forward, I think there are some exciting directions that this whole line of work could go in. If it's easy to generate a concurrent data structure, then can we start thinking about workload-specific concurrent data structures, whether it's thinking specifically about skew or taking into account properties of keys, or recognizing that most priority queues have far fewer priorities than they have elements, so maybe a heap isn't the right data structure to be focused on. It's also important to combine these ideas with other essential performance dimensions. I don't think I talked at all today about locality. And while locality wouldn't matter to skip hash CRUD operations, it certainly would help range queries. And lastly, I think we all need to recognize that distributed memory is not something that we can ignore. And if we have 1 microsecond remote memory access latencies, and we're operating in an environment where 1 kilobyte data transfers cost the same as 16 byte data transfers, then thinking about locality and seeking constant time operations, exploring the value of double linking, these are all things that are going to pay off in spades, because when the cost of each memory access is so high, anything we can do to reduce the number of memory accesses and to get these improvements that are asymptotic is going to pay off, because the constants are just so huge. So to wrap up, I want to, first of all, thank you for the opportunity to talk today. I especially want to thank Fastcode for existing and for wanting to help all programmers and all universities to have programs in place and opportunities for students and practitioners to learn the importance of writing fast code. Alan Perlis once said, "A programming language is low level when its programs require attention to the irrelevant." And I'm very grateful that Fastcode understands and is proclaiming that performance is not irrelevant and that it demands attention. I also want to thank my collaborators listed here and to the financial supporters who I'm sure don't agree with any of my conclusions, but supported the work nonetheless. And so with what remaining time we have, I'd love to hear any questions anyone has or converse about anything that's on your minds. Thank you.
Thank you, Mike. We do have a question already in the chat. And yeah, if there are more questions, please put them in the chat. This is from Ajay. Thanks for the great talk, Mike. What reclamation algorithm did you use in the experiments?
Oh, good question. Yeah, we just used a very basic timestamp SMR sort of thing, where since we were already using the RDTSCP, it was really easy to just use that to timestamp objects as they were being reclaimed. Nothing sophisticated, nothing fancy. Certainly a place where I'm sure you could probably squeeze 5% more performance out by using one of your fancy algorithms, Ajay.
Any other questions?
Bruce, let me go next. I have a quick question for Mike. It's more out of curiosity. I mean, when we work on transactional memory, there were 2 ways of using it. One is using for designing the structures, and the other one is to synchronize programs, which might have the structures inside, but you want to synchronize other modifications. So I love your talk, because it's exactly what Fastcode tries to do, which is teaching, improving the way we write complex programs and make it accessible. So you're advocating for, so at that time we were saying black box, we can do both. So you're saying no, open the box to see what's inside, expose even metadata to programmers, but not to the end programmer, right? To the designers of the structure, which is still an object, which is a very strong semantics and strict semantics implemented. So what about the rest? What about the others? What about the programmers that want to write a concurrent programs, not as specific to the structures? They want to synchronize data accesses, and they're still thinking about STM, but with all the performance and bad implications that you discuss. Have you thought about it? Because we can't expose metadata to those programmers. That's a disaster. So, so what do you think it's what we can do in that space? Which I think, Fastcode would like to cover those as well.
I think the verdict is still out on that, Roberto. It's a great question. I'm inclined to lean towards the direction that Idish Kedar and Eddie Kohler have been going in, with like transactional data structure libraries and adding like transactional semantics on top of concurrent data structures. We have certainly found in some unpublished work that if we use ideas like those that I presented today in those kinds of implementations, we can cut back on the overhead quite a bit. And so it's pretty exciting and appealing, but that's just one direction to go in. I also can't help but think about that famous quotation that, you know, the two biggest mistakes engineers make are optimizing too early and generalizing too early. And in the same way as the early transactional memory benchmarks maybe weren't realistic of what people actually wanted transactions for, I'm not sure that we really have that killer app yet for the
Right.
problem that you're describing.
Right.
And so like we can optimize TPCC and YCSB all day, but I don't know in the end if that's what the world is really in need of. But it's a great question and a great opportunity for future work.
Thanks, Mike.
Thank you.
Thank you, Mike, again for a great talk. I don't see any more questions, but if people have, excuse me, if people have questions, Mike, do you want to say anything about like welcoming follow-up from people, or how they should be following up on ideas stimulated by your talk?
I'm really open to what you think is the best way to go. Do we have like a great blog or wiki or something where people, or there's a Slack, right? There's a fast code Slack. We could use that. I don't know. It's whatever people feel most comfortable with. If something in this talk is interesting to you and you want to pursue collaborations, if you want to keep them private, you can email me. If you think it's more appropriate for the community to be involved in a conversation, whatever works for you. I'm not a picky person.
Great comments. So I promise that in the next couple weeks, I will be writing a blog post on this, and in the next newsletter that'll go out. And that will be a place, that would be sort of a public place. And the private channel, I'm sure would like your email. So we'll make that happen. And with that, I think we're done for this month's Fast Code seminar. Thank you very much, Mike. Thanks, Roberto, for hosting. We'll be back in July when Renato's going to be giving a talk. So thanks, everybody. Have a great summer.
Great. Thank you very much.
Thank you, Mike.